There is a star 129 light-years from Earth that has broken our understanding of how worlds are born. It is a young star, barely 30 million years old, still surrounded by the dust and debris of its own creation. And around it, 4 enormous planets are locked in a gravitational dance so impossibly precise that for years, scientists suspected their own instruments were deceiving them. Each of these planets is larger than Jupiter. Each orbits at distances that stretch the limits of what our models can explain. And each one has been seen, not inferred from a wobble, not deduced from a shadow, not calculated from a dip in brightness, seen, photographed, captured in infrared light that crossed 129 years of empty space before landing on the mirrors of our most powerful telescopes. This is HR 8799. It is the most important planetary system that most people have never heard of, and it has shattered assumptions that stood unchallenged for decades. Consider what it takes to photograph a planet around another star. Stars are blindingly bright. A typical star outshines its planets by a factor of 1 million or more in visible light. Trying to see a planet beside its parent star is like trying to spot a single candle flame next to a raging bonfire from a distance of several thousand kilometers. The candle is there, its photons are real, but they are hopelessly overwhelmed by the inferno beside them. For most of the history of astronomy, directly seeing an exoplanet was considered not merely technically difficult, but fundamentally impossible. The glare was too great. The separations were too small. The contrast was too extreme. We could detect planets indirectly, by watching for the faint dimming as they transited their star, or by measuring the subtle gravitational tug they imposed on it. But capturing their actual light, isolating their faint glow from the overwhelming brilliance of their sun, was a challenge that seemed to place a hard ceiling on what observation could achieve. And then, in 2008, a team of astronomers pointed 2 of the most sophisticated telescopes on Earth at an unremarkable star in the constellation Pegasus. What they found defied every expectation and opened a door that can never be closed. They did not find one planet. They found 3. Within a year, a 4th was confirmed. 4 massive gas giants, all orbiting the same young star, all captured in a single field of view. It was the first time in the entire history of our species that multiple planets had been directly photographed around another star. The announcement electrified the astronomical community, not merely because the planets existed, but because they existed where they should not have been. They were too far from their star. They were too massive. They were too perfectly spaced. The system looked almost designed, as though someone had placed each world with geometric intention. No one had, of course. Nature built this arrangement through physics alone. But the question of how has consumed planetary scientists for nearly 2 decades. And the deeper we investigate, the stranger and more troubling the answers become. Each new observation peels back another layer, and beneath each layer lies another mystery waiting to be confronted. What does it mean when reality defies our theories? What does it mean when a planetary system exists in a configuration our models call unstable, yet it has clearly persisted for tens of millions of years without tearing itself apart? What does it mean when the process of planet formation, a process we spent half a century developing and refining and testing, turns out to be far more mysterious and far more flexible than anyone suspected? These are not idle questions. They are not the kind of questions that can be set aside and revisited later. They go to the heart of our understanding of how the cosmos builds its architecture, how matter organizes itself across the vast distances of interstellar space, and how the chain of events that ultimately led to our own existence fits into a larger and far more complex pattern than we ever imagined. By the end of tonight, you're going to understand why this single star system, this one faint point of light in a sky containing hundreds of billions of others, has forced a rethinking of the fundamental rules that govern how worlds come into being. You will understand the staggering difficulty of seeing what was once invisible, the ingenuity that made it possible, and the profound uncertainty that still remains. And you will confront a truth about our place in the cosmos that is as humbling as it is beautiful. Before we get started, if you love exploring the depths of space as much as we do, Take a second to like the video or subscribe. It is a simple action, but it helps this channel reach more curious minds like yours. This is a story about 4 worlds that should not exist, orbiting a star that reveals more with every observation in a configuration that challenges the deepest assumptions of modern planetary science. It is a story about what happens when the universe refuses to follow the script we have written for it. And it begins with a question that is simple to ask and extraordinarily difficult to answer. How do you see something that is, by every reasonable measure, invisible? Now let's begin. To understand why HR 799 matters so deeply, we first need to understand the problem it solved and the far larger problem it created. And that means stepping back to look at the enormous challenge of finding planets around other stars. A challenge that occupied astronomers for centuries before a single confirmed discovery was made. For most of human history, the only planets we knew about were the ones in our own solar system: Mercury, Venus, Mars, Jupiter, Saturn. These bright wandering lights in the night sky were our entire catalogue of known worlds. Uranus was added in 1781 by William Herschel, an amateur astronomer who stumbled upon a new planet while conducting a systematic survey of the heavens. Neptune followed in 1846, discovered not by observation but by mathematics. Urbain Le Verrier, a French mathematician, predicted Neptune's existence and position based on unexplained perturbations in the orbit of Uranus. Johann Galle at the Berlin Observatory pointed his telescope to the predicted location and found the planet within 1 degree of where Le Verrier said it would be. It was one of the great triumphs of Newtonian mechanics. And for more than a century after that, the count of known planets stood still. 8 worlds, 1 star, 1 solar system. The question of whether other stars harboured planets of their own was a subject of philosophical speculation and informed guesswork, but not of observational science. Many astronomers believed exoplanets existed. The laws of physics that govern the formation of our solar system are universal. The same gravity, the same gas dynamics, the same chemistry that built our worlds should operate around every other star. There was no reason to think our sun was special, but belief is not evidence, and the technical barriers to finding exoplanets were formidable. Stars are luminous, planets are dim, the distances are immense, the angular separations are tiny. Even with the most powerful telescopes of the 20th century, detecting a planet around another star seemed to require instruments that did not yet exist and techniques that had not yet been invented. The first confirmed detection of an exoplanet around a sun-like star came in 1995, and it arrived like a thunderclap. Michel Mayor and Didier Queloz, 2 astronomers working at the Haute-Provence Observatory in southern France, announced the discovery of a planet orbiting 51 Pegasi, a sun-like star about 50 light-years from Earth. The planet, designated 51 Pegasi b, was nothing like anyone had predicted. It had roughly half the mass of Jupiter, but it completed 1 orbit around its star in just 4.2 days. This impossibly short orbital period meant the planet was orbiting at a distance of only about 0.05 astronomical units from its star, roughly 7.5 million kilometers. For comparison, Mercury, the innermost planet in our solar system, orbits the Sun at about 0.39 astronomical units, nearly 8 times farther out. At such extreme proximity, the surface temperature of 51 Pegasi b would have exceeded 1,000 degrees Celsius. The planet was a bloated, roasting gas giant, a type of world that existed in no theoretical prediction and no simulation. It came to be called a hot Jupiter, and its very existence was an affront to the orderly picture of planet formation that prevailed at the time. Mayor and Queloz would eventually share the 2019 Nobel Prize in Physics for this discovery, a recognition of just how profoundly it changed our view of the cosmos. The method they used is called radial velocity, or the Doppler wobble technique. The underlying principle is beautifully simple. Every planet exerts a gravitational pull on its parent star. As the planet orbits, it pulls the star in a tiny circle or ellipse. When the star moves toward Earth, even by a few meters per second, its spectral lines shift slightly toward the blue end of the spectrum. When it moves away, the lines shift toward the red. By measuring these spectral shifts with extreme precision, using instruments called high-resolution Ishel spectrographs, astronomers can detect the gravitational signature of an orbiting planet. From the amplitude of the wobble, they infer the planet's minimum mass. From the period of the wobble, they determine the orbital period. The technique is powerful and has been used to discover hundreds of exoplanets since 1995. But it is entirely indirect. You never see the planet, you see its effect on the star. You see its shadow in the data. The planet itself remains invisible. The second major detection method, and the one responsible for the largest number of confirmed exoplanets, is the transit technique. A transit occurs when a planet passes directly between its star and our line of sight, casting a tiny shadow that causes the star's brightness to dip. For a Jupiter-sized planet crossing a Sun-like star, the brightness decrease is roughly 1%. For an Earth-sized planet, the decrease is about 0.01%, a change so minuscule that it requires space-based instruments of exquisite sensitivity to detect. But what the transit method lacks in ease, it makes up for in information. The depth of the brightness dip tells you the planet's physical radius. The duration tells you something about the orbital geometry, and by combining the radius with a mass measurement from radial velocity, you can calculate the planet's average density, which reveals whether it is made of rock, ice, gas, or some combinations. NASA's Kepler Space Telescope, launched in March of 2009, was designed specifically to exploit the transit method on a grand scale. It stared at a single patch of sky in the constellations Cygnus and Lyra, monitoring roughly 150,000 stars continuously for 4 years, watching for the telltale brightness dips that signal a transiting planet. Kepler was nothing short of a revolution. It discovered over 2,700 confirmed exoplanets during its primary and extended missions. It revealed worlds of every conceivable type, gas giants in tight orbits, rocky planets in habitable zones, worlds orbiting binary stars, planets smaller than Earth, and planets larger than Neptune but smaller than Jupiter, a class we now call sub-Neptunes, which turned out to be the most common type of planet in the galaxy. Kepler also demonstrated a statistical truth that reshaped our understanding of the cosmos. Planets are not rare, they are ubiquitous. Analysis of Kepler's data showed that, on average, every star in the Milky Way has at least one planet. Some have 2, 3, 5 or more. The galaxy, with its roughly 400 billion stars, harbours even more planets than stars. As of the most recent count, more than 5,700 confirmed exoplanets have been catalogued across all detection methods, with tens of thousands of additional candidates awaiting verification. The universe, far from being empty and barren, is teeming with worlds. The question is no longer whether planets exist around other stars. The question is what they are like, how they formed, and whether any of them harbour conditions suitable for life. But here is the problem. Both radial velocity and the transit method share a fundamental limitation. They tell you that a planet exists. They tell you its mass, or its radius, or its orbital period, or its density. They do not show you the planet. They do not let you see it as a distinct point of light, separated from the glare of its star. They do not let you analyze its atmosphere directly, measure its thermal emission, detect weather patterns in its cloud layers, or track its position as it moves through its orbit year after year. For all of that, you need a fundamentally different approach. You need direct imaging. And direct imaging of exoplanets is, by virtually any standard, one of the most difficult technical achievements in the history of science. To understand why, consider this comparison. Imagine you are standing on the eastern coast of the United States, looking westward. 3,000 kilometers away on the Pacific coast, someone holds a lit match directly next to a lighthouse beam. Your task is to photograph the match, not the lighthouse, just the match. You must separate the feeble glow of the match from the blinding glare of the lighthouse beside it. Even though, from your vantage point, 3,000 kilometers away, the two light sources appear to overlap almost completely. That, in rough terms, is the challenge. The star is the lighthouse, the planet is the match, and from Earth, the angular distance between them is so small that it would take the most advanced optics ever constructed to resolve them as separate objects. The contrast ratio makes the problem even more extreme. In visible light, a Sun-like star outshines a Jupiter-like planet by a factor of roughly 1 billion. That means for every photon arriving from the planet, 1 billion photons arrive from the star. In the near-infrared, where most direct imaging is conducted, the contrast improves to roughly 100,000 to 1 for a young, self-luminous giant planet. This is better, but still enormous. Suppressing 100,000 stellar photons for every planetary photon requires technology of almost absurd precision. The first essential technology is adaptive optics. Earth's atmosphere is turbulent. Rising columns of warm air, descending pockets of cold air, and wind shear at various altitudes all conspire to bend and distort the incoming starlight. This is why stars twinkle. To the naked eye, twinkling is charming. To an astronomer trying to image a faint companion next to a bright star, it is catastrophic. The atmospheric turbulence smears the star's image into a fuzzy blob many times larger than the theoretical resolution of the telescope, burying any companion's signal beneath a wash of scattered light. Adaptive optics systems correct this in real time. A wavefront sensor measures the atmospheric distortion, typically by analyzing the light from a bright reference star or an artificial laser guide star many hundreds of times per second. This information is fed to a deformable mirror, a thin reflective surface controlled by hundreds or thousands of tiny pistons called actuators. The mirror continuously adjusts its shape to cancel the atmospheric distortion, restoring the sharpness of the image to near the diffraction limit of the telescope. The technology is remarkable, and it is essential for direct imaging. The second essential technology is coronagraphy. A coronagraph is a specialized optical element that blocks the light from a central star while allowing fainter light from nearby sources to pass through. The concept was invented in 1930 by French astronomer Bernard Liot, who designed the first solar coronagraph to observe the sun's corona, its tenuous outer atmosphere, without waiting for a total solar eclipse. Modern stellar coronagraphs are far more sophisticated. They use precisely shaped masks, apodized apertures, and interference effects to suppress the central starlight over a carefully controlled range of angular separations. Even so, no coronagraph is perfect. Residual starlight leaks through, creating a pattern of bright speckles in the image that can easily be mistaken for real astronomical objects. The third essential technology is computational post-processing. After adaptive optics has sharpened the image and a coronagraph has blocked most of the starlight, the resulting images still contain far too much residual glare to reveal a planet directly. This is where ingenious data processing becomes indispensable. The technique that proved decisive for HR 8799 is angular differential imaging, developed by Christian Marois and his collaborators. In this method, the telescope tracks a star over an extended period while the instrument rotator is held fixed, allowing the sky to rotate relative to the detector. Any real object in the sky, such as a planet, rotates with the sky, while instrumental artifacts, including residual speckles from the star, remain stationary. By constructing a model of the static speckle pattern, subtracting it from each image, and then derotating and co-adding the residual frames, the signal from a genuine companion can be extracted from the noise. The technique demands long observations, exquisite calibration, and deep expertise in image analysis, but it works. Marois and his team chose their target with scientific precision and strategic foresight. They needed a star that was young, because young planets still retain the heat of their formation and glow brightly in the infrared. A gas giant that formed 30 million years ago might be 1,000 degrees hotter than the same planet would be after 4 billion years of cooling. That extra heat translates directly into extra brightness, making young planets far easier to detect. They needed a star that was nearby, so that the angular separations of any companions would be large enough to resolve. They needed a star whose brightness was sufficient for the adaptive optics system to lock onto, but not so great that it overwhelmed the coronagraph. And they wanted a star with independent evidence of a planetary system, such as the infrared excess that signals a circumstellar debris disk. HR 8799 satisfied every requirement perfectly. The star is classified as an F-type main sequence star, meaning it is somewhat hotter, more massive, and more luminous than our Sun. Its mass is approximately 1.5 times solar. Its luminosity is roughly 4.9 times greater. Its spectral characteristics place it firmly on the main sequence, the stage of stellar life, where a star burns hydrogen in its core, the same stage our Sun has occupied for the past 4.6 billion years. HR 8799 sits at a distance of 129 light-years in the constellation Pegasus. 129 light-years sounds vast by human standards, but it is practically next door in galactic terms. The Milky Way spans roughly 100,000 light-years across its disk. If you compress the galaxy so that it fit inside a large sports stadium, say one with a diameter of 300 meters, the distance from the Sun to HR 8799 would be less than half a millimeter. We are neighbors. The star's age is estimated at approximately 30 million years. Our Sun, by contrast, is about 4.6 billion years old. That makes the Sun roughly 153 times older. If you compressed the Sun's entire lifetime into a single 24-hour day, from its birth to the present, HR 8799 would have formed less than 10 minutes before midnight. It is a newborn star in every sense. Its planets are still glowing with the residual warmth of their creation, radiating heat generated by gravitational contraction and accretion. This residual heat is what makes them visible. Without it, they would be cold, dark, and undetectable with any technology we currently possess. Before the direct imaging observations, the star had already attracted attention. Infrared space telescopes, including the Spitzer Space Telescope, detected excess thermal emission from HR 8799, a classic signature of a circumstellar debris disk. Follow-up observations with sub-millimeter and millimeter telescopes revealed a complex disk architecture. A warm inner dust belt, analogous to our solar system's asteroid belt, occupies a region roughly 6 to 10 astronomical units from the star. A cold outer dust belt, analogous to our Kuiper belt, extends from approximately 90 astronomical units to beyond 300 astronomical units. Between these two belts lies a broad, relatively clear gap, spanning the region from about 10 to 90 astronomical units. The gap was the critical clue. Debris disks do not spontaneously develop wide gaps. Something massive had to be clearing that space, gravitationally perturbing or ejecting the dust and debris. Something with the gravitational authority of a giant planet. Or perhaps several. In November of 2008, Christian Marois and his team published their results in the journal Science. The paper was titled Direct Imaging of Multiple Planets Orbiting the Star HR 8799. Using data from both the Keck 2 telescope and the Gemini North telescope at the summit of Mauna Kea in Hawaii, at an altitude of roughly 4,200 meters above sea level, they presented clear images of 3 planets. The planets were labeled B, C, and D, following the convention that assigns letters in order of discovery. Planet B, the outermost and first detected, orbits at approximately 68 astronomical units from the star. Planet C sits at roughly 38 astronomical units. Planet D is found at about 24 astronomical units. Each planet was estimated to have a mass between 5 and 10 times that of Jupiter, depending on which evolutionary cooling model was used to convert the observed brightness into a mass. The following year, 2009, a 4th planet was identified. HR 8799e, the innermost, orbits at approximately 14.5 astronomical units. To put these distances in perspective, consider our own solar system. Jupiter orbits at about 5.2 astronomical units, Saturn at about 9.5, Uranus at roughly 19.2, Neptune at approximately 30. The innermost planet of HR 8799 orbits at a distance comparable to the region between Saturn and Uranus in our system. The outermost orbits at more than twice the distance of Neptune. These are enormous orbital radii, and each planet occupying them is a gas giant dwarfing anything in our neighborhood. Here is a scaled comparison to make the system tangible. If the star HR 8799 were the size of a grapefruit, sitting on a table in front of you, planet E would be a small marble placed about 12 meters away. Planet D would be another marble at roughly 20 meters. Planet C would sit at about 32 meters. And planet B would be a marble placed 57 meters away, across the room and out the door, down the hallway, and possibly around the corner. At that scale, each marble represents a world 5 to 10 times the mass of Jupiter. The distances between them are enormous relative to the star. The system is vast, majestic, and governed by gravitational interactions of tremendous complexity. The discovery electrified the field. 4 directly imaged planets around a single star. The images themselves, showing 4 faint dots arranged around a bright central point, became iconic in astronomy, reproduced in textbooks, popular articles, and conference presentations worldwide. But the excitement was tempered by a growing sense of unease, because the system, beautiful as it was, posed a problem. A deep problem. The 4 planets, with their large masses and wide orbits, appeared to exist in a configuration that our theoretical models predicted should be unstable. Gravitational interactions between bodies that massive, orbiting that close together in relative terms, should have disrupted the system long ago. Planets should have been flung out. Orbits should have been scrambled. The neat, almost symmetrical arrangement should have dissolved into chaos within a few million years. Yet the system endures. It has survived for 30 million years. The explanation, researchers concluded, must lie in an orbital resonance, a precise mathematical relationship between the orbital periods of the 4 planets. The leading candidate is a 1 to 2 to 4 to 8 chain, where each planet's orbital period is roughly twice that of the next planet inward. This resonance, if real, would act as a stabilizing mechanism, preventing the gravitational interactions from growing chaotic. The planets would tug on each other, yes, but always in a rhythmic, coordinated way that preserves the overall architecture rather than destroying it. The question that followed was inevitable and enormously difficult. How did the resonance chain form? How did 4 massive planets find themselves in such a precise dynamical arrangement? What physical processes, operating in the first few million years of the system's life, produced this specific outcome and no other? To appreciate the difficulty of the question, consider another scaled comparison. Imagine 4 heavy bowling balls placed on a vast, slightly curved trampoline. Each ball warps the surface around it, and the warping caused by one ball affects the motion of the others. If the balls are placed carelessly, they roll toward each other, collide, or tumble off the edge. Only a very precise set of positions and velocities allows all 4 to orbit the center of the trampoline indefinitely, each one rising and falling in coordination with the others, never crashing, never escaping. The HR 8799 system is that trampoline. The planets are the bowling balls. And the question is not merely whether this configuration can exist, because it does, but how nature managed to place each ball with such unerring accuracy. The resonance chain also carries a timestamp. Resonances of this kind do not form instantaneously. They develop over time, as planets migrate through their nascent disk and are captured into resonance one by one. The innermost pair locks first, then the next planet is captured, and then the next, building the chain link by link. The process requires specific disk conditions, specific migration rates, and specific timing. If any element is off, the chain does not form, or it forms but shatters. The fact that the chain exists today, intact after 30 million years, means that every step of its assembly went right. Every migration converged, every capture held, every perturbation was damped. The system is not merely stable. It is the product of a formation process that, by all indications, had very little room for error. This is deeply strange. In most areas of astrophysics, the universe is forgiving. Small changes in initial conditions lead to small changes in outcomes. A slightly more massive star burns slightly faster but lives a qualitatively similar life. A slightly different orbit produces a slightly different climate but not a fundamentally different planet. HR 8799 seems to defy this principle. Its existence appears to depend on conditions that were not merely favorable but precise, and that precision demands explanation. The answers to these questions reach into the deepest and most contested territory in all of planetary science, and what astronomers discovered as they began to probe the formation history of this remarkable system was worse than anyone expected. The standard model of planet formation is called core accretion. It is the dominant theory in planetary science, supported by decades of observation, simulation, and theoretical development. It explains how our own solar system formed. It explains the formation of most known exoplanets. And HR 8799 breaks it. Core accretion works like this. A young star forms from a collapsing cloud of molecular gas and dust. As the cloud contracts under its own gravity, Conservation of angular momentum causes it to flatten into a rotating disk, a structure called a protoplanetary disk. This disk is composed primarily of hydrogen and helium gas, with a small but crucial admixture of heavier elements, silicates, iron, water ice, carbon compounds, the raw materials of solid planets. Within the disk, microscopic grains of dust begin to collide and stick together, a process called coagulation. The grains grow from submicrometer particles to millimeter-sized aggregates, then to centimeter-sized pebbles, then to meter-sized boulders. This growth continues through further collisions and gravitational attraction, building larger and larger bodies. When these bodies reach sizes of roughly 1 kilometer across, they are called planetesimals. Planetesimals interact gravitationally, colliding and merging, growing through a process called oligarchic growth. Over millions of years, a few dominant bodies emerge. Protoplanetary cores tends to hundreds of times the mass of Earth. When a rocky or icy core reaches a critical mass, estimated to be around 10 Earth masses, something dramatic happens. The core's gravity becomes strong enough to capture and retain large quantities of hydrogen and helium gas from the surrounding disk. Gas flows onto the core, slowly at first, then with increasing speed as the growing envelope attracts more and more material. This runaway gas accretion phase is rapid, potentially doubling the planet's mass in just thousands of years. The result is a gas giant, a planet with a dense rocky or icy core surrounded by an enormous envelope of light gases. This is how Jupiter is thought to have formed, roughly 5 astronomical units from the young Sun, where the disk was dense enough and cold enough for water ice to condense, providing ample solid material for core growth. The boundary in the disk where water transitions from vapor to ice, known as the snow line or ice line, is critical. Beyond the snow line, the abundance of solid material roughly doubles, because water ice adds to the silicate and iron grains that are available everywhere. This doubling dramatically accelerates core growth, which is why the giant planets in our solar system formed beyond about 3 astronomical units, where the snow line lay in the early solar nebula. Saturn formed farther out at about 9.5 astronomical units. Uranus and Neptune, the ice giants, formed at even greater distances, though their smaller masses suggest they barely managed to accrete gas envelopes before the disk dissipated. The process of core accretion is well understood in its broad strokes, well simulated on supercomputers, and well supported by observations of protoplanetary disks around young stars in nearby star-forming regions. It is the default framework for understanding planetoid formation. It works. At least, it works in the inner and middle regions of the disk, where material is abundant and orbital timescales are short. The question is whether it works everywhere. But here is the critical constraint. The protoplanetary disk does not last forever. It has a finite lifetime, set by the balance between the rate at which material is supplied and the rate at which it is removed. Observations of young stellar systems in nearby star-forming regions, such as the Taurus-Auriga molecular cloud, the Rho-Ophiuchi complex, the Orion Nebula cluster, and the Scorpius-Centaurus association, provide clear evidence that protoplanetary disks typically dissipate within roughly 3 to 10 million years after the star forms. Surveys at infrared and submillimeter wavelengths show that the fraction of stars with detectable disks drops sharply with age. By 5 million years, roughly half of all disks are gone. By 10 million years, fewer than 10% remain. The gas is dispersed by several mechanisms. The star's ultraviolet and X-ray radiation heats the upper layers of the disk, driving material away in a thermal wind through a process called photoevaporation. Gas is also gradually accreted onto the star itself, drawn inward by the viscous stresses within the disk. Interactions with nearby stars in the birth cluster can strip material from the outer disk through tidal encounters, and the energetic radiation environment of the cluster can externally photoevaporate the disk from the outside in. The end result is that the disk, and with it the raw material for building gas giant planets, vanishes within a few million years. Once the gas is gone, no more gas giants can form. The window is finite. The clock is ticking from the moment the star ignites, and it waits for no planet. Now consider the planets of HR 8799. The innermost, planet E, orbits at 14.5 astronomical units from the star. That is nearly 3 times the orbital distance of Jupiter in our solar system. At 14.5 astronomical units, the disk is significantly less dense than it is at 5 astronomical units. There is less solid material available for building cores, and the orbital timescales are longer, meaning fewer collisions per unit time. Building a 10 Earth mass core at this distance is possible within the standard model, but it is slow. Planet D orbits at 24 astronomical units, Planet C at 38. These distances are comparable to the orbits of Uranus and Pluto in our solar system, regions where the disk density drops steeply and the timescales for core growth stretch toward the upper limits of the disk's lifetime. And then there is Planet B, the outermost, orbiting at 68 astronomical units. At 68 astronomical units, the protoplanetary disk is sparse, cold, and thinly spread. The density of solid particles is a tiny fraction of what it is in the inner disk. The orbital period at this distance is roughly 460 years. In the 3 to 10 million years that the disk exists, Planet B completes only 6,500 to 22,000 orbits. Each orbit provides an opportunity for the growing core to encounter and accrete material, but at 68 astronomical units, there is simply not enough material to encounter. The reservoir of solids is too small, the feeding zone is too wide. The timescale for building a massive core at this distance, under the assumptions of standard core accretion, is on the order of 100 million years or more. The disk lasts 10 million years at best. The planet should not be able to form before its building material disappears. To be direct about it, there is not enough time and not enough material to build a 5 to 10 Jupiter-mass planet at 68 astronomical units through core accretion. The mathematics does not work. This is not a minor shortfall or a marginal inconsistency. It is an order of magnitude failure. The formation timescale exceeds the disk lifetime by a factor of 10 or more. The theory predicts that Planet B cannot exist where it is found, yet it does, and it gets worse. The problem is not confined to Planet B alone. Planets C and D, at 38 and 24 astronomical units respectively, also push the boundaries of what core accretion can achieve. The timescales are shorter at those distances, yes, but still uncomfortably long, particularly when you consider that 4 giant planets must all form within the same limited window. Building one gas giant in the outer disk is hard. Building 4, at 4 different distances, all within a few million years, strains the theory to its breaking point and beyond. The system does not merely challenge core accretion. It stands in direct contradiction to its most basic predictions. This contradiction is where the second major theory of planet formation enters the story. It is called gravitational instability, sometimes referred to as disk instability or top-down formation. The idea is conceptually the opposite of core accretion. Instead of building planets from the bottom up, grain by grain, pebble by pebble, rock by rock, gravitational instability proposes that planets can form from the top down, collapsing directly from the gas and dust of the disk. The mechanism works as follows. If a protoplanetary disk is sufficiently massive and sufficiently cold, it can become gravitationally unstable. Density fluctuations in the disk, small overdense regions, caused by turbulence or tidal interactions, can grow under their own gravity faster than the disk's internal pressure can smooth them out. When this happens, the disk fragments. Clumps of gas and dust collapse into self-gravitating objects, protoplanets or proto-brown dwarfs, on very short timescales. How short? Hundreds to thousands of years, perhaps as few as a single orbital period at the relevant distance. This is extraordinarily fast compared to the millions of years required by core accretion. A Jupiter-mass planet could form from disk instability in the time it takes a human civilization to rise and fall. In cosmic terms, it is nearly instantaneous. For the HR 8799 system, gravitational instability is immediately attractive. It solves the timescale problem at a stroke. Planets at 68 astronomical units, no difficulty. The disk fragments quickly, long before it has a chance to dissipate. Planets at 24, 38, 68 astronomical units. All of them can form simultaneously, in different regions of the disk, within the first 100,000 years. The speed is there. The distances are right. On the surface, disk instability seems like the obvious answer. But the theory has deep and unresolved problems of its own. The first problem is the disk mass requirement. For a disk to become gravitationally unstable, it must be massive. Specifically, the disk mass must be a significant fraction of the stellar mass, typically 10% or more. For HR 8799, with a stellar mass of about 1.5 solar masses, this means the disk would have needed to contain at least 0.15 solar masses, equivalent to roughly 150 Jupiter masses, or approximately 50,000 Earth masses. This is an enormous amount of material. Observations of protoplanetary disks around young stars show that most disks are far less massive than this. Typical disk masses range from 1 to 10% of the stellar mass. A disk at the 10% threshold is at the extreme upper end of the observed distribution. It is possible but unusual. Disk instability requires conditions that are not common. The second problem is fragment survival. Even if the disk is massive enough to fragment, the fragments are not guaranteed to survive. Simulations of gravitationally unstable disks show that newly formed clumps are subject to intense forces. Tidal interactions with the central star stretch and deform them. Interactions with each other can lead to mergers or ejections, and many clumps, perhaps the majority, migrate rapidly inward through the disk due to gravitational torques, spiraling toward the star and being consumed before they can contract into stable, bound objects. The survival rate of disk fragments is highly uncertain and depends sensitively on the disk's thermodynamic properties, particularly its ability to cool. If the disk cools efficiently, fragments contract quickly and survive. If cooling is slow, fragments are sheared apart before they can collapse. The boundary between these two regimes is sharp and poorly constrained. The third problem is the mass spectrum. Gravitational instability tends to produce massive objects. The characteristic fragment mass depends on the local conditions of the disk, particularly the temperature and density, but it is typically in the range of several to tens of Jupiter masses, or even higher. Many simulations produce objects in the brown dwarf regime, 13 to 80 Jupiter masses, rather than the planetary regime. Producing objects specifically in the 5 to 10 Jupiter mass range, which is where the HR 8799 planets appear to sit, requires fine-tuning the disk conditions. The temperature must be cold enough for fragmentation, but not so cold that the fragments become too massive. The density must be high enough for instability, but not so high that the fragments merge into a single massive object. The parameter space is narrow. The fourth problem is chemical composition. This is perhaps the most promising avenue for distinguishing between the two formation mechanisms, but also the most technically challenging. Planets formed by core accretion should have compositions that are enriched in heavy elements relative to their host star. The reason is straightforward. During core accretion, the growing core preferentially accumulates metals, silicates, and ices from the disk. These heavy elements are incorporated into the core itself and, during the gas accretion phase, are mixed into the surrounding envelope. The result is a planet whose overall composition, and particularly whose atmospheric composition, has a higher ratio of heavy elements to hydrogen and helium than the star from which it formed. In our own solar system, Jupiter's atmosphere is enriched in heavy elements by a factor of roughly 3 to 4 relative to the Sun. Saturn's enrichment is even greater, about 7 to 8 times solar. These enrichments are strong evidence that both planets formed through core accretion. Planets formed by gravitational instability, on the other hand, should have compositions that closely mirror the composition of the star. The reason is equally straightforward. In disk instability, a clump of gas and dust collapses directly from the bulk material of the disk. There is no preferential accumulation of heavy elements. No rocky core forms first. The planet is essentially a small piece of the disk that became gravitationally bound. Its composition should therefore be indistinguishable from the star's, with the same ratio of heavy elements to hydrogen and helium. The carbon to oxygen ratio is one of the most diagnostic measurements. In a protoplanetary disk, carbon and oxygen are distributed differently. Water ice, which is oxygen-rich, condenses at the snow line and is available for core accretion in the outer disk. Carbon-bearing species, such as carbon monoxide and methane, have different condensation temperatures and are distributed differently through the disk. A planet that formed by core accretion in a specific region of the disk may have a carbon-to-oxygen ratio that is distinctly different from the star's, depending on where in the disk it accreted its material. A planet that formed by disk instability should have a carbon-to-oxygen ratio identical to the star. Spectroscopic observations of the HR 8799 planets have been conducted by numerous research groups using ground-based instruments such as the Gemini Planet Imager, the SPHERE instrument at the European Southern Observatory's Very Large Telescope, and integral field spectrographs on the Keck and Subaru telescopes. The results are suggestive but not definitive. Some studies have reported evidence for elevated carbon-to-oxygen ratios in one or more of the planets, potentially indicating chemical processing consistent with core accretion or hybrid formation. Others have found compositions that are closer to stellar values, which would favor disk instability. The atmospheric models used to interpret the spectra are complex and laden with assumptions about cloud properties, chemical equilibrium, vertical mixing, and photochemistry. Different teams analyzing overlapping data sets with different modeling frameworks have reached different conclusions. The James Webb Space Telescope, with its unprecedented infrared sensitivity and spectral coverage, has the potential to resolve this debate, but the analysis of its early observations of HR 8799 is still ongoing. The definitive chemical fingerprint of these planets' formation remains elusive, so we are left with a profound and frustrating impasse. Core accretion, the theory that explains the formation of most known planets in our galaxy, cannot build the HR 8799 planets fast enough. Gravitational instability can build them fast enough, but may not produce the right kind of planets in the right mass range, and it requires disk conditions that lie at the extreme end of what is observed. Neither theory, in its standard form, fully explains what we see. Something is wrong with our assumptions. Either the protoplanetary disk around HR 8799 was far more massive and far more structured than typical disks, or the planets formed at different locations and migrated to their current positions through a process we do not yet fully understand, or some hybrid mechanism was at work that combined elements of both theories in a way that current simulations cannot reproduce. Or there is physics that we have not yet incorporated into our models. Each of these possibilities has been explored. None has been proven. The migration hypothesis deserves particular attention because it introduces its own set of complications. In many simulations of young planetary systems, planets do not remain where they form. They interact gravitationally with the surrounding disk, exchanging angular momentum and gradually shifting their orbits. This process, called planetary migration, is well established in the theory of planet formation. Hot Jupiters, those gas giants that orbit their stars in just a few days, are almost certainly products of inward migration. They formed much farther from their stars, in the cold outer regions of the disk, where gas giant formation is viable, and then spiraled inward through disk interactions until they reached their current locations. Could the planets of HR 8799 have formed closer to the star, where core accretion timescales are manageable, and then migrated outward to their present positions? The idea is seductive because it removes the timescale problem entirely. If the planets formed at 5 to 15 astronomical units, core accretion could have built their cores within the disk's lifetime without difficulty. The question then becomes whether the planets could have migrated outward after forming. This is where the idea encounters resistance. Outward migration is much harder to achieve than inward migration. The dominant mode of planet-disk interaction, known as Type II migration for gap-opening giant planets, acts to drain angular momentum from the planet and send it spiraling inward. This is why hot Jupiters end up so close to their stars. The disk acts as a brake, slowing the planet's orbital motion and causing it to fall toward the star. Reversing this process, pushing a planet outward against the natural flow of angular momentum transfer, requires special circumstances. Outward migration can occur when two planets are locked in a mean motion resonance, and the torque balance between the disk and the inner planet is sufficient to push both outward. It can also occur if the disk has a particular radial density or temperature profile that generates a positive torque on the planet. In certain simulations, the transition between the optically thick inner disk and the optically thin outer disk creates a torque reversal zone, a location where migration naturally changes direction. If a planet forms near this zone, it can be pushed outward rather than inward, but producing 4 planets that all migrate outward in concert to the right distances, maintaining a resonance chain throughout the entire process, requires an extraordinarily specific set of initial conditions and disk properties: the disk mass, the viscosity parameter, the temperature gradient, the opacity structure, the initial locations of the planets, and the timescale of disk dispersal must all fall within narrow ranges. Change any one of these parameters by a modest amount, and the migration proceeds differently. The planets end up in the wrong places, or the resonance chain fails to capture them, or one or more planets spiral into the star. The fine-tuning problem is unavoidable. The fine-tuning problem is a recurring theme in the study of HR 8799. At every turn, the system seems to demand conditions that are precise rather than typical, special rather than generic. The masses must be within a narrow range. The orbits must satisfy a specific resonance chain. The disk must have had the right mass, the right temperature profile, and the right viscosity. The migration must have been at the right rate, in the right direction, for the right duration. Any deviation, and the system would not exist as we see it. There is another layer of complexity that must be addressed, one that transforms this problem from merely difficult to genuinely profound. The dynamical stability of the system itself is a deep puzzle. 4 massive planets, relatively closely spaced in astronomical terms, interact gravitationally with one another in ways that are highly nonlinear and potentially chaotic. In the field of celestial mechanics, a discipline with roots stretching back to Isaac Newton in the 17th century, through Pierre-Simon Laplace in the 18th and Henri Poincaré in the 19th, the gravitational interaction of multiple bodies has been a source of endless fascination and frustration. The two-body problem, one planet orbiting one star, has an exact mathematical solution. The orbit is an ellipse, it repeats forever. The three-body problem, 2 planets orbiting one star, has no general closed-form solution. The system must be integrated numerically, step by step, and the behavior can range from stable and predictable to wildly chaotic depending on the masses and initial conditions. The 4-body problem, 3 planets and a star, is worse still, and the 5-body problem, 4 planets and a star, which is the case for HR 8799, is extraordinarily complex. Small changes in the masses or orbital parameters can lead to vastly different outcomes over time, a hallmark of chaotic dynamics. When researchers first applied numerical integration codes to the HR 8799 system using the initially published mass estimates and orbital elements from the 2008 and 2009 discovery papers, the results were deeply disturbing. Most configurations were unstable. Within a few million simulated years, one or more planets would experience a close gravitational encounter with another, resulting in a violent scattering event. Planets would be flung onto highly eccentric orbits, ejected from the system entirely, or sent plunging inward toward the star. The neatly ordered configuration observed in the images dissolved into chaos almost immediately. In dynamical terms, the system appeared to be a house of cards, ready to collapse at the slightest disturbance. This was deeply troubling because the system has not collapsed. It is 30 million years old and counting. It has clearly endured far longer than the simulations predicted it should. The resolution came with the recognition that the system must be in, or very close to, a mean motion resonance chain. Mean motion resonances are a well-known phenomenon in celestial mechanics. They occur whenever the orbital periods of 2 bodies are related by a ratio of small whole numbers. In our own solar system, Pluto and Neptune are in a 3-to-2 resonance, meaning Pluto completes exactly 2 orbits for every 3 orbits of Neptune. This resonance prevents Pluto from ever coming close enough to Neptune to be gravitationally perturbed out of its orbit, even though the 2 objects' orbits actually cross in space. The resonance is protective. It keeps the bodies in phase, ensuring that their close approaches happen at the same relative orbital positions, where the geometry of the interaction is stabilizing rather than destabilizing. For the HR 8799 system, the best fitting scenario is a 1 to 2 to 4 to 8 resonance chain. Planet B orbits once for every 2 orbits of planet C. Planet C orbits once for every 2 orbits of planet D. Planet D orbits once for every 2 orbits of planet E. The ratios are all 2 to 1, cascading through the system from outside to inside. This is known as a Laplace-like resonance chain, named after Pierre-Simon Laplace, who first described the analogous three-body resonance among Jupiter's moons Io, Europa, and Ganymede. In that system, for every orbit Ganymede completes, Europa completes 2 and Io completes 4. The 1 to 2 to 4 relationship keeps the three moons synchronized in perpetuity. HR 8799 extends this principle to 4 planets, adding another link to the chain. This resonance chain is extraordinary. It means the orbital periods of the 4 planets are in the ratio 1 to 2 to 4 to 8. If planet B takes 460 years to orbit, planet C takes about 230 years, planet D takes about 115 years, and planet E takes about 57 years. The synchronization is precise enough that gravitational interactions remain bounded, preventing the runaway instabilities that would otherwise tear the system apart. It is the dynamical equivalent of 4 pendulums swinging in perfect phase, each one's motion reinforcing the stability of the others. But even with the resonance, the margins are knife-thin. Comprehensive dynamical studies, such as those conducted by Daniel Fabrici and Ruth Murray Clay at the Harvard-Smithsonian Center for Astrophysics, and by Thane Curry and collaborators at the Subaru Telescope, have tested millions of orbital configurations. The conclusion is consistent across studies. The system is stable only within an extremely narrow range of masses and orbital parameters. Increase the mass of any single planet by 15 to 20%, and the resonance breaks. Shift the eccentricity of any orbit by a small fraction, and the system becomes chaotic. The configuration that allows long-term survival occupies a tiny island of stability in a vast ocean of instability. The system is balanced on a razor's edge. This fragility carries information. It tells us that whatever process formed this system did not just create 4 giant planets. It created 4 giant planets with the right masses, in the right orbits, with the right eccentricities, and the right resonant relationships, all within the narrow tolerances that permit long-term survival. The formation process was not just successful, it was precise, and explaining that precision is the central challenge of HR 8799 science. The problem extends far beyond this one system, and that is what makes it so important. HR 8799 is not just a curiosity about 1 star and 4 planets. It is a test case for the entire framework of planet formation theory. If our models cannot explain how 4 giant planets formed and survived in this specific configuration, then the models are incomplete. And if the models are incomplete for this system, they may be incomplete for many others as well. How many planetary systems exist in configurations that our theories would predict to be impossible? How many have we failed to find simply because we were not looking in the right way, or because our expectations blinded us to the possibilities? What fraction of the true diversity of planetary systems lies outside the range of what our models can currently account for? These are not idle academic questions. They cut to the heart of how well we understand the process that built our own world. Earth exists because a specific sequence of events unfolded during the formation of the solar system. The Sun's protoplanetary disk had a particular mass, a particular composition, a particular temperature profile. Planets formed at particular distances, with particular masses, through particular mechanisms. If any of those parameters had been different, the solar system would look different. Earth might not exist, we might not exist. And if our understanding of those parameters and those mechanisms is less complete than we thought, then our understanding of our own origins is less secure than we believed. The Milky Way contains roughly 400 billion stars. Current estimates suggest that at least 20% of Sun-like stars have a planet in the habitable zone, but the fraction that host multiple giant planets in wide, resonant orbits remains unknown. It could be relatively common, with most such systems simply too faint and too distant to detect with current instruments. It could be vanishingly rare, a 1 in a million configuration that we happened to discover because it was nearby, bright and young? The answer has profound implications. If systems like HR 8799 are common, it means our theoretical framework is missing something fundamental. If they are rare, it means the conditions required to build such a system are extraordinary, and understanding those conditions becomes all the more urgent. But here's what makes this truly terrifying. We have studied planet formation for more than half a century. We have discovered thousands of exoplanets across a stunning range of sizes, masses, orbits, and compositions. We have built computer models of extraordinary sophistication that simulate the birth and evolution of planetary systems, from the physics of individual dust grains to the dynamics of entire stellar nurseries. And yet one system, one single collection of 4 planets around one ordinary young star, has revealed gaps in our understanding so wide and so deep that they may take generations to close. The universe is not required to conform to our expectations. It does not grade us on effort. It simply exists in all its bewildering complexity. And HR 8799 is the proof that our picture of that complexity is still profoundly incomplete. Part 4. The search for answers. So the problem is clear. 4 giant planets, too massive and too far from their star to be explained by core accretion in its standard form. Too precisely arranged to be the product of gravitational instability in its simplest incarnation. Too delicately balanced to be the result of random chance. Since the initial discovery in 2008, the scientific community has launched an extraordinary effort to understand this system, deploying every observational, computational, and theoretical tool at its disposal. The story of that effort is a story of ingenuity, frustration, and incremental progress. It is also a story that is still being written. The first and most obvious avenue of investigation was to refine the observations themselves. The discovery images, as groundbreaking as they were, provided only a snapshot, 4 bright dots around a star, captured at a single moment in time. From those images, astronomers could measure the apparent separations of the planets from the star and estimate their brightnesses. But they could not directly measure masses. They could not measure orbital velocities. They could not determine whether the planets were moving clockwise or counterclockwise. The orbital periods of these planets range from roughly 50 years for the innermost to roughly 460 years for the outermost. So the fraction of each orbit that has been observed since 2008 is small. Planet E has completed perhaps a third of its orbit. Planet B has traced less than a 20th. Determining precise orbital parameters from such incomplete arcs is like trying to reconstruct the shape of an entire racetrack from watching a car drive a few hundred meters along the straightaway. Nevertheless, the community set about doing exactly that. In the years following the discovery, Christian Mawar and his collaborators, along with numerous independent research groups, obtained additional epochs of imaging data. Each new observation added another data point to the measured positions of the 4 planets. By 2012, 4 years after the discovery, a handful of astrometric positions were available for each planet. By 2016, the time baseline had extended to 8 years, and by 2020 to 12 years. Each new measurement tightened the constraints on the orbital parameters, slowly revealing the shape and orientation of each planet's path through space. The process of fitting orbits to these data is computationally demanding and fraught with degeneracies. From the measured positions alone, without radial velocity information, there are families of orbits that are equally consistent with the data. An orbit that appears circular when viewed face-on could also be an eccentric orbit viewed at a particular angle. An orbit that appears to have a specific semi-major axis could be a slightly larger orbit viewed at a different inclination. To break these degeneracies, researchers employ Bayesian statistical techniques, exploring vast parameter spaces using Markov chain Monte Carlo methods and other sampling algorithms. They generate millions of candidate orbital solutions, each characterized by a set of 6 orbital elements for each of 4 planets, plus 4 masses, giving a total of 28 free parameters. They then evaluate each solution against the data, keeping those that fit the observed positions and rejecting those that do not. But the orbital fitting alone is not sufficient. This is where the dynamical stability constraint becomes a powerful additional filter. Most of those millions of candidate orbital solutions, even the ones that perfectly match the observed positions, are dynamically unstable. They lead to planetary collisions or ejections within a few 100,000 years, which is far less than the system's estimated age of 30 million years. By requiring that the orbital solution be stable for at least 30 million years, researchers can eliminate the vast majority of candidate solutions and dramatically narrow the range of acceptable orbital parameters. This approach, which combines astrometric orbit fitting with dynamical stability analysis, was pioneered by several groups working independently. The results converged on a consistent picture. The planets are most likely in nearly circular orbits, with eccentricities below about 0.1. The orbital plane is inclined at roughly 20 to 30 degrees from our line of sight. The masses are constrained to lie within a relatively narrow range, roughly 5 to 10 times the mass of Jupiter for each planet, with the outermost planet likely being the least massive of the four. And the system is most consistent with the 1 to 2 4 to 8 resonance chain described earlier. Although the evidence for exact resonance, as opposed to near resonance, remains a subject of active debate. The distinction between exact resonance and near resonance is subtle but important. In an exact resonance, the orbital period ratios are precisely 2 to 1, and the resonant angles, which are specific combinations of the planet's orbital longitudes, oscillate around fixed values. This oscillation, called libration, is the hallmark of a true resonance. It means the planets are locked together dynamically, their orbits coupled by the resonance like gears in a machine. In a near resonance, the period ratios are close to 2 to 1, but not exact, and the resonant angles circulate rather than librate. The planets are near the resonance, but not trapped in it. Near resonance systems can still be stable for long periods, but they lack the protective dynamical coupling that exact resonances provide. Determining whether the HR 8799 planets are in exact resonance or merely near resonance requires orbital measurements of extraordinary precision. The difference between a period ratio of exactly 2.000 and a ratio of 1.98 or 2.02 is small, but it makes a qualitative difference to the dynamical behavior of the system. Current observations are not yet precise enough to definitively distinguish between these possibilities. The orbital arcs are too short, the measurement uncertainties too large, but the trend of the data, combined with the dynamical stability requirement, strongly favors exact or very near exact resonance for all four planet pairs. While the orbit fitting community was refining the dynamical picture, a parallel effort was underway to characterize the physical properties of the planets themselves, particularly their atmospheres. This is where direct imaging provides a unique advantage over other detection methods. When a planet is detected by the radial velocity or transit method, we learn about its mass and radius, but the planet itself is lost in the glare of the star. We cannot separate its light from the star's light. We cannot spread its light into a spectrum. We cannot measure the composition of its atmosphere. Direct imaging changes this entirely. Because the planet's light has been spatially separated from the star's light, it can be independently analyzed. The first atmospheric studies of the HR 8799 planets were conducted using broadband photometry, measuring the total brightness of each planet through a series of color filters spanning the near-infrared spectrum. These measurements revealed that the planets are red, much redder than expected for objects of their temperature and mass. In astrophysics, color is a proxy for atmospheric composition and cloud structure. A clear, cloud-free atmosphere allows light to emerge from a range of depths, producing a spectral energy distribution that reflects the temperature and composition of the atmosphere in a relatively straightforward way. But the unusually red colors of the HR 8799 planets indicated that their atmospheres are not clear. They are cloudy, blanketed by thick layers of condensate particles that scatter and absorb light in ways that dramatically alter the emerging spectrum. The nature of these clouds has been a subject of intense investigation. At the temperatures of the HR 8799 planets, roughly 800 to 1200 Kelvin, The atmospheric chemistry is expected to produce clouds of iron and silicate particles. Yes, iron clouds. Droplets and grains of molten iron, condensing out of the atmosphere like water droplets in an earthly cloud, forming opaque layers that shroud the deeper atmosphere from view. The silicate clouds are equally exotic, composed of particles of enstatite, forsterite, and other magnesium silicate minerals, familiar to geologists as the building blocks of Earth's mantle. But here suspended in a swirling alien atmosphere, thousands of degrees cooler than the furnaces where we encounter them on Earth. These clouds create enormous complications for atmospheric modeling. The size distribution of the cloud particles, their vertical extent, their optical properties, and their interaction with atmospheric dynamics all affect the emergent spectrum. Different cloud models, with different assumptions about particle size and cloud thickness, can fit the same data equally well, but imply very different atmospheric compositions. This degeneracy between cloud properties and atmospheric composition is one of the central challenges of exoplanetary atmospheric science, and the HR 8799 planets are among the most affected objects. Despite these challenges, significant progress has been made. Low-resolution spectra of the planets, obtained using integral field spectrographs on the Gemini, Keck, and Subaru telescopes, have revealed the presence of water vapor and carbon monoxide in the atmospheres of at least planets B and C, and probably D and E as well. Methane, which should be abundant at these temperatures according to chemical equilibrium models, has proven more difficult to detect. In several analyses, its abundance appears to be lower than expected, a phenomenon known as chemical disequilibrium. Chemical disequilibrium occurs when vertical mixing in the atmosphere dredges up material from hotter, deeper layers, where carbon monoxide is the dominant carbon-bearing species, faster than the chemical reactions can convert it to methane in the cooler upper atmosphere. The presence of chemical disequilibrium provides information about the vigor of atmospheric circulation, the rate of vertical mixing, and the temperature structure of the deep atmosphere, all of which are difficult to constrain by other means. The Gemini Planet Imager and the SPARE instrument at the Very Large Telescope, both of which came online in the mid-2010s, represented a major advance in the characterization of the HR 879 planets. These second-generation high-contrast imaging instruments combine adaptive optics, coronagraphy, and integral field spectroscopy into a single optimized system, designed from the ground up for the detection and characterization of directly imaged planets. They achieve contrast levels that are an order of magnitude better than the first-generation instruments used in the discovery, and they provide spatially resolved spectra across a range of near-infrared wavelengths in a single observation. GPI observations of HR 8799C and D, published by researchers including Jason Wang, Jeffrey Chilcote, and their collaborators at the University of California, Berkeley, and the Dunlap Institute for Astronomy and Astrophysics in Toronto, provided the highest quality spectra of these planets obtained from the ground. The spectra showed clear absorption features from water vapor, constrained the effective temperatures and surface gravities of the planets, and provided new constraints on the carbon-to-oxygen ratio. The measured carbon-to-oxygen ratios were broadly consistent with stellar values, but the uncertainties were large enough that elevated ratios, which would favor certain core accretion scenarios, could not be excluded. The SPHERE observations, led by researchers at institutions across Europe, including the Max Planck Institute for Astronomy in Heidelberg, the Institute for Planetology and Astrophysics of Grenoble, and the Leiden Observatory, complemented the GPI data by extending the spectral coverage to slightly longer wavelengths and providing independent measurements of the photometric and spectroscopic properties of the planets. The combined picture that emerged from these studies is tantalizing but incomplete. The planets have thick, cloudy atmospheres dominated by hydrogen and helium, with detectable water vapor and carbon monoxide, and possibly reduced methane abundance indicating chemical disequilibrium. Their effective temperatures range from roughly 800 Kelvin for the outermost planet to roughly 1200 Kelvin for the innermost. Their surface gravities are consistent with masses of 5 to 10 Jupiter masses. depending on the assumed age of the system and the evolutionary models used to convert luminosity to mass. But the key chemical diagnostics that could discriminate between formation mechanisms, particularly the precise carbon-to-oxygen ratio and the atmospheric metallicity, meaning the overall abundance of elements heavier than hydrogen and helium, remain frustratingly uncertain. Enter the James Webb Space Telescope. Launched in December 2021 and fully operational by mid-2022, JWST represents the most significant advance in infrared astronomical capability since the Spitzer Space Telescope, and perhaps the most transformative observatory since Hubble. Its 6.5-meter primary mirror, its location at the second Lagrange point 1.5 million kilometers from Earth, and its suite of infrared instruments covering wavelengths from 0.6 to 28 microns make it the ideal tool for studying the atmospheres of directly imaged planets. JWST observed the HR 8799 system during its first year of science operations. The observations used the near-infrared camera, known as NIRCam, and the mid-infrared instrument, known as MIRI, to image the planets at wavelengths that are inaccessible from the ground due to atmospheric absorption. At mid-infrared wavelengths, between 5 and 28 microns, the thermal emission from the planets is stronger relative to the star, and the spectral features of key molecular species, including ammonia, phosphine, and various carbon and nitrogen-bearing compounds, become accessible for the first time. These species are of particular interest because their abundances are highly sensitive to atmospheric temperature, pressure, and mixing, and they carry information about the planet's bulk composition and formation history that cannot be obtained from near-infrared observations alone. The JWST coronagraphic observations of HR 8799 have been eagerly anticipated by the exoplanet community, but the analysis is complex and ongoing. The coronagraphs on JWST were designed primarily for detecting and characterizing planets at smaller angular separations than the HR 8799 planets, and their performance at the relatively large separations of this system is excellent. However, the subtraction of the stellar point spread function, the calibration of the photometry, and the modeling of the detector systematics all require careful analysis. Early results, presented at conferences and in preprint form, suggest that JWST has detected all 4 planets with high signal-to-noise ratio at multiple wavelengths, and that the mid-infrared photometry reveals new features in the spectral energy distributions that were not accessible from the ground. The full exploitation of the JWST data for HR 8799 will take years. The spectral energy distributions must be compared with grids of atmospheric models spanning a range of temperatures, gravities, compositions, and cloud properties. The chemical abundances must be retrieved using sophisticated statistical retrieval frameworks that account for the correlations between different atmospheric parameters. The results must be compared with predictions from planet formation models to determine which formation pathway, if any, is consistent with the observed compositions. This is painstaking work, requiring the combined expertise of atmospheric modelers, spectroscopists, statisticians, and planet formation theorists. It is work that is underway as these words are written in research groups around the world, and its outcome may reshape our understanding of how giant planets form. Parallel to the atmospheric characterization efforts, a major theoretical campaign has been waged to understand the formation of the HR 8799 system through numerical simulation. This effort has involved some of the most sophisticated computational tools in astrophysics, including smoothed particle hydrodynamics codes that simulate the gas dynamics of protoplanetary disks, N-body integrators that trace the gravitational interactions of multiple planets over millions of years, and hybrid codes that combine both approaches to model the full life cycle of a planetary system from disk to debris. The formation simulations have explored a vast parameter space. Different groups have investigated different formation mechanisms, different disk models, different initial conditions, and different physical assumptions. The question they all share is the same. Can we produce a system that looks like HR 8799, with 4 giant planets in the right orbits, with the right masses, in a stable resonance chain, formed within the lifetime of a protoplanetary disk. The core accretion simulations, conducted by groups at institutions including the University of Bern, the University of Nice, the University of Victoria, and the Carnegie Institution for Science, have explored the possibility that the planets formed closer to the star and migrated outward. In these models, the protoplanetary disk is seeded with one or more planetary embryos at distances of 5 to 15 astronomical units, where the timescale for core accretion is short enough to build massive cores within the disk lifetime. The embryos grow by accreting solid material and then gas, eventually reaching masses of several Jupiter masses. As they grow, they interact gravitationally with the disk, opening gaps in the gas and exchanging angular momentum. In some configurations, the interactions between the planets and the disk, and between the planets themselves, drive outward migration, expanding the orbits while maintaining or establishing resonant relationships. These simulations have achieved partial success. They can produce systems with 4 giant planets in wide orbits, and they can produce resonance chains. But matching all the observed properties of HR 8799 simultaneously has proven extraordinarily difficult. The models that produce the right orbital separations tend to produce the wrong masses. The models that produce the right masses tend to produce the wrong resonance chain. The models that produce the right resonance chain tend to require disk properties that are at the edge of or beyond the observed range. No single simulation has produced a convincing HR 8799 analog that matches all the observational constraints. The parameter space is large, and the number of simulations that can be run is limited by computational resources, so it is possible that the right combination of initial conditions simply has not yet been tried. But the persistent difficulty of matching all the constraints simultaneously suggests that something more fundamental may be at work. The disk instability simulations have faced equally daunting challenges. Groups at institutions, including the Max Planck Institute for Astronomy, the Scottish Universities Physics Alliance, and the University of Central Lancashire, have modelled the gravitational fragmentation of massive protoplanetary disks using high-resolution hydrodynamic codes. These simulations resolve the three-dimensional structure of the disk, tracking the formation and evolution of self-gravitating clumps from the initial fragmentation through the subsequent contraction, accretion, and dynamical evolution. The results are mixed. Disk instability can indeed form giant planet mass objects at wide orbital separations, and it can do so quickly, within a few thousand years of the onset of fragmentation. But the objects that form tend to be more massive than the HR 8799 planets, often in the range of 10 to 30 Jupiter masses, straddling the boundary between giant planets and brown dwarfs. The objects also tend to form at random locations in the disk, without any preferred spacing or resonant relationship. Producing 4 objects in a resonance chain purely through disk instability requires additional mechanisms, such as tidal interactions with the remaining disk gas, to bring the fragments into resonance after formation. These mechanisms can work in principle, but they add additional free parameters and additional layers of fine-tuning. A third approach, which has gained traction in recent years, is the hybrid formation scenario. In this picture, the protoplanetary disk around HR 8799 was massive enough for gravitational instability to operate in the outer regions, but not massive enough for the resulting clumps to grow into brown dwarfs. Instead, the clumps contracted and accreted only a limited amount of gas before the disk dispersed, ending up with masses in the range of 5 to 10 Jupiter masses. The inner planets, closer to the star, may have formed by core accretion, taking advantage of the shorter formation timescales at smaller radii. Migration and resonance capture then brought all 4 planets into their current configuration. This hybrid scenario is appealing because it does not require either theory to do all the work. Each mechanism operates in the regime where it is most effective, and the final system is the product of their combined action. But the hybrid scenario is also the hardest to test, because it has the most free parameters and the most complex interplay between different physical processes. It requires specifying not only the initial disk mass temperature and density profile, but also the location and timing of gravitational fragmentation in the outer disk, the accretion history of the inner cores, the migration rates of all 4 planets, the timing and mechanism of resonance capture, and the dispersal of the disk gas. Each of these processes has its own uncertainties and its own model dependencies, constraining all of them simultaneously. From observations of a system that is 30 million years old and has long since lost any direct trace of its protoplanetary disk is a formidable challenge. Beyond the formation question, the community has also invested considerable effort in searching for systems analogous to HR 8799. If similar systems exist around other stars, their properties could provide crucial context for understanding the formation mechanism. A single system is anecdotal. A population of similar systems would be statistical, and statistics are the foundation of science. The search for HR 8799 analogues has been conducted using both direct imaging surveys and indirect methods. Direct imaging surveys, such as the Gemini Planet Imager Exoplanets Survey and the Sphere Survey for Exoplanets, have observed hundreds of young nearby stars, searching for planetary mass companions at wide orbital separations. These surveys have discovered a handful of directly imaged planets, including the remarkable system around the star Beta Pictoris, which hosts 2 giant planets detected by both direct imaging and radial velocity. But no system has been found that is a close analogue of HR 8799. 4 giant planets in a resonance chain at wide orbital separations around a young star. The occurrence rate of such systems appears to be low, probably less than a few percent of young, nearby Sun-like and A-type stars. This low occurrence rate is itself a clue. It tells us that whatever conditions are required to form a system like HR 8799 are not common. The typical protoplanetary disk does not produce this outcome. Something unusual must have occurred. An unusually massive disk, an unusually efficient fragmentation process, an unusually precise migration history, or some combination of these factors. The rarity of the outcome constrains the formation mechanism. Any viable theory must explain not only how HR 8799 formed, but also why systems like it are so uncommon. The comparison with Beta Pictoris is particularly instructive. Beta Pictoris is in many ways the closest analogue to HR 8799 that has been found. It is a young A-type star, somewhat more massive and more luminous than HR 8799. Located at a distance of about 63 light-years. It has a prominent debris disk that has been imaged in exquisite detail, and it hosts 2 known giant planets, Beta Pictoris b, at a distance of about 9 astronomical units, with a mass of roughly 11 Jupiter masses, and Beta Pictoris c, at about 2.7 astronomical units, with a mass of roughly 8 Jupiter masses. The 2 planets are not in a resonance with each other, and their orbital separations are much smaller than those of the HR 8799 planets. The system is different in detail, but the broad similarities, a young star with a debris disk and multiple giant planets, make it a valuable point of comparison. Other systems with directly imaged planets include PDS-70, a young T Tauri star with 2 protoplanets still embedded in their natal disk, caught in the act of formation. The PDS-70 system is extraordinary because it provides direct observational evidence for planet formation in progress, with the protoplanets accreting material from the surrounding disk and carving visible gaps in the dust distribution. But the system is at a much earlier evolutionary stage than HR 8799, and the final masses and orbits of the protoplanets are not yet determined. The connection between systems like PDS-70, which show planet formation in progress, and systems like HR 8799, which show the finished product, is a key area of ongoing research. The wider context of exoplanetary science also provides important constraints. The thousands of planets discovered by the Kepler mission and ground-based surveys have revealed that small planets, super-Earths, and mini-Neptunes with radii between 1 and 4 times that of Earth are the most common type of planet in the galaxy. Giant planets like Jupiter and Saturn are relatively rare, occurring around perhaps 10 to 15% of Sun-like stars. Multiple giant planets in the same system are rarer still, and multiple giant planets in wide orbits, beyond 10 astronomical units, are the rarest of all because they are the hardest to detect, and because the conditions required for their formation are the most restrictive. This statistical context shapes the interpretation of HR 8799. The system is not just unusual, it is an outlier, occupying the extreme tail of the distribution of planetary system architectures. Understanding outliers is often where the deepest insights lie. The physics that produces the typical case may be well understood. The physics that produces the extreme case often reveals new mechanisms, new parameter regimes, or new processes that were not anticipated by the standard theory. HR 8799 is precisely such a case. Its extreme properties push our theories to their limits and beyond, and in doing so, they reveal the boundaries of our current understanding. The effort to understand HR 8799 has also driven technological innovation. The need for better contrast, better angular resolution, and better spectral coverage has motivated the development of new instruments and new observing techniques. The choreographic wavefront sensing algorithms developed for GPI and SPARE have been refined and improved based on lessons learned from observations of HR 8799 and other directly imaged systems. The post-processing algorithms, such as angular differential imaging, spectral differential imaging, and principal component analysis-based methods, have become increasingly sophisticated, achieving contrast levels that were unimaginable a decade ago. These improvements benefit not just the study of HR 8799, but the entire field of high-contrast imaging, enabling the detection of fainter and closer companions around other stars. Looking ahead, the next generation of ground-based telescopes, the Giant Magellan Telescope, the 30-meter telescope, and the Extremely Large Telescope, will provide another leap in capability. With primary mirrors ranging from 24 to 39 meters in diameter, these telescopes will achieve angular resolutions that are 3 to 5 times better than current 8 to 10 meter telescopes, and they will collect far more light, enabling spectroscopy of planets that are currently too faint to characterize. For the HR 8799 system specifically, these telescopes will provide spectral coverage and signal-to-noise ratios that will enable definitive measurements of the atmospheric compositions, including the carbon-to-oxygen ratios and metallicities that hold the key to distinguishing between formation mechanisms. The Extremely Large Telescope, currently under construction in the Atacama Desert of Chile by the European Southern Observatory, is expected to see first light in the late 2020s. Its 39-meter segmented primary mirror will make it the largest optical and infrared telescope ever built. When equipped with its planned high-contrast imaging instruments, it will be able to detect planets at separations and contrasts that are inaccessible to any existing facility. For HR 8799, the ELT will be able to obtain medium-resolution spectra of all 4 planets, potentially resolving individual spectral lines and measuring atmospheric velocities, temperatures, and compositions with unprecedented precision. The combination of JWST in space and the ELT on the ground will create a synergy that is greater than the sum of its parts. JWST provides access to wavelengths that are blocked by Earth's atmosphere, while the ELT provides angular resolution that JWST with its 6.5-meter mirror cannot match. Together, they will enable a complete characterization of the HR 8799 planets that would be impossible with either facility alone. The atmospheric compositions, the thermal structures, the cloud properties, and the chemical disequilibrium signatures will all be measured with sufficient precision to make definitive statements about the formation history of this remarkable system. But even with these powerful new tools, some questions may remain unanswered. The formation of the HR 8799 system occurred 30 million years ago, and the protoplanetary disk that gave rise to the planets has long since dispersed. The direct evidence of the formation process, the disk mass, the temperature structure, the density profile, the location and timing of planet formation is gone. What remains are the planets themselves, their orbits, their masses, their atmospheres, and the debris disk that surrounds them. These are the forensic clues, the fingerprints left at the scene. Reconstructing the crime from the fingerprints is possible, but it requires extraordinary care and a certain tolerance for ambiguity. The history of this system may never be known with certainty, but the effort to understand it has already yielded insights that extend far beyond one star and 4 planets. It has challenged our theories, driven our technology, and expanded our imagination. And that is the hallmark of truly great science. There is one more thread of investigation that deserves attention before we move on, and it concerns the debris disk that surrounds the HR 8799 system. The debris disk, first detected through excess infrared emission by the Infrared Astronomical Satellite in the 1980s, and subsequently imaged in detail by the Spitzer Space Telescope, the Herschel Space Observatory, and the Atacama Large Millimeter Array, is not a single structure, but 2 distinct components separated by a wide gap. The inner component, a warm belt of dusty material, lies between roughly 6 and 15 astronomical units from the star, interior to the orbit of the innermost planet, HR 8799e. The outer component, a cold belt analogous to the Kuiper belt in our solar system, extends from roughly 90 to at least 300 astronomical units, well beyond the orbit of the outermost planet, HR 8799b. The gap between the 2 belts, spanning roughly 15 to 90 astronomical units, corresponds precisely to the region occupied by the 4 planets. This correspondence is not coincidental. The gravitational influence of the 4 planets sweeps this region clean of debris, preventing dust and small bodies from accumulating in stable orbits. The inner edge of the outer belt and the outer edge of the inner belt are sculpted by the gravitational perturbations of the outermost and innermost planets, respectively. The sharpness of these edges provides additional constraints on the masses and orbital eccentricities of the planets, independent of and complementary to the constraints derived from direct imaging astrometry. The debris disk is also a tracer of the system's collisional history. The dust that we observe in the 2 belts is not primordial. It is not left over from the protoplanetary disk that existed during the era of planet formation. That disk dispersed within the first 10 million years of the system's life, driven away by the combined effects of accretion onto the star and planets, photoevaporation by stellar radiation, and clearing by the planet's gravitational influence. The dust we see today is second-generation material produced by the ongoing collisional grinding of larger bodies, asteroids and comets, that have survived since the epoch of planet formation. These parent bodies, ranging in size from kilometers to hundreds of kilometers, are too small to detect individually, but their presence is inferred from the dust they produce. The rate of dust production, combined with the rate at which radiation pressure and other forces remove dust from the system, tells us about the total mass and size distribution of the parent body population, which in turn tells us about the early solid content of the protoplanetary disk. Observations with the Atacama Large Millimeter Array have resolved the outer debris belt with sufficient angular resolution to measure its radial and azimuthal structure. The belt appears to be relatively smooth and axisymmetric, without the prominent clumps or warps that would indicate ongoing dynamical perturbation by an unseen 5th planet beyond the known 4. This places an upper limit on the mass of any additional planet beyond planet B, constraining it to be no more than roughly 1 to 2 Jupiter masses at distances beyond 100 astronomical units. The smoothness of the belt also suggests that the system has reached a state of relative dynamical equilibrium, with the 4 known planets dominating the gravitational architecture and no major unseen perturbers lurking in the outer reaches. The 2-component debris disk structure is itself a remarkable parallel to our own solar system, which has the asteroid belt between Mars and Jupiter and the Kuiper belt beyond Neptune. In both cases, the gap between the belts is maintained by the gravitational influence of giant planets. The analogy is imperfect, because the HR 8799 system is scaled up in virtually every dimension. More massive planets, wider orbits, a more luminous star. But the architectural similarity is suggestive. It hints that the fundamental processes of planetary system formation, the interplay between planet formation, planet migration, and debris clearing, produce similar large-scale structures across a range of stellar masses and system scales. The details differ, but the broad strokes rhyme. and in those rhymes there may be clues to the universal principles that govern how planetary systems are built. Part 5. What it means for everything. There is a temptation, when studying a single extraordinary system, to treat it as an isolated puzzle. Here are 4 planets, here are their properties. Figure out how they formed, move on. But HR 8799 resists that kind of compartmentalization, because the questions it raises do not stop at the boundary of its own debris disk. They ripple outward, touching every corner of the field of planetary science, and ultimately reaching the most fundamental question we can ask about the universe we inhabit. How common is our own existence? To understand the significance of this system, we must first confront a fact that the astronomical community has been grappling with for 3 decades. Our solar system is not typical. For most of human history, we assumed that other planetary systems, if they existed, would resemble our own, small rocky planets close to the star, gas giants farther out. Nice orderly orbits, nearly circular, nearly coplanar, widely spaced. This was not a prediction derived from first principles, it was a bias born of having only one And when the first exoplanets were discovered, beginning with the detection of a giant planet around 51 Pegasi in 1995, the bias was shattered almost immediately. The planet around 51 Pegasi orbits in just over 4 days, at a distance of about 0.05 astronomical units from its star. It has roughly half the mass of Jupiter, a giant planet closer to its star than Mercury is to our Sun. This was not supposed to be possible. In the solar system, giant planets exist only beyond the snow line, the distance from the star at which water condenses to ice, which in our system lies at roughly 3 astronomical units. Inside the snow line, there was insufficient solid material to build the massive cores needed to capture gas envelopes. Giant planets were supposed to be an outer solar system phenomenon, and yet there was 51 Pegasi b, a giant planet practically brushing the surface of its star. In the decades that followed, the catalogue of known exoplanets grew from a handful to hundreds to thousands, and the diversity of planetary system architectures proved to be staggering. Hot Jupiters like 51 Pegasi b were just the beginning. There were super-Earths, planets with masses between Earth and Neptune that have no analogue in our solar system, and yet turned out to be the most common type of planet in the galaxy. There were mini-Neptunes, slightly larger than super-Earths, but still far smaller than the ice giants of our outer solar system. There were systems with multiple planets packed into orbits tighter than Mercury's, their years measured in days. There were eccentric giants, Jupiter-mass planets on wildly elongated orbits that sweep from close to the star to the frozen outer reaches. There were circumbinary planets, orbiting 2 stars locked in their own mutual orbit, a geometry once dismissed as dynamically impossible. Against this backdrop of extraordinary diversity, our own solar system stands out for its orderliness. Our rocky planets are small and widely spaced. Our gas giants are in nearly circular orbits at large distances. We have no hot Jupiters, no super-Earths, no planets inside Mercury's orbit or between Mars and Jupiter. We are, by the standards of the exoplanetary census, unremarkable and yet distinctly unusual. The architecture of our solar system is not the default. It is one possibility among many, shaped by a specific set of initial conditions and a specific sequence of events that could easily have produced a very different outcome. HR 8799 adds another dimension to this picture. It shows us a planetary system architecture that is extreme even by the standards of the exoplanet population. 4 giant planets in wide orbits, locked in a resonance chain, with a 2-component debris disk, around a young luminous star. This is not a slight variation on the theme of our solar system. This is a fundamentally different outcome, produced by fundamentally different conditions, or possibly by fundamentally different physics. And it forces us to ask how many other fundamentally different outcomes exist that we have not yet discovered, simply because we lack the tools to detect them. The observational limitations are severe and worth examining in detail, because they shape everything we think we know about the prevalence of systems like HR 8799. Direct imaging, the only method that can detect planets at the orbital separations of the HR 8799 system, is sensitive only to young, massive, self-luminous planets around nearby stars. A planet that has cooled to the point where its thermal emission is faint, as all 4 HR 8799 planets will eventually do is invisible to current direct imaging surveys. A system identical to HR 8799 but 10 times more distant would be undetectable. A system identical to HR 8799 but 10 times older would be undetectable. A system with planets only twice as massive as Jupiter, rather than 5 to 10 times as massive, would be at the very edge of detectability. This means that the sample of directly imaged planets is profoundly biased toward the most extreme cases, the most massive air planets, around the youngest and nearest stars at the widest orbital separations. HR 8799 is not just a remarkable system that happened to be found. It is a system that was found precisely because it is remarkable. Its planets are massive enough, hot enough, and distant enough from a bright enough star that they could be detected with the technology available in 2008. A more modest system with smaller planets or a smaller star or a greater distance would have been invisible. The question is not why HR 8799 was found. The question is how many similar systems exist that we cannot see. The answer depends on the underlying distribution of planetary system architectures, which is exactly what we are trying to determine. It is a frustrating circularity. We want to know how common systems like HR 8799 are, but we can only detect the most extreme examples, and we cannot reliably extrapolate from the extreme examples to the broader population without knowing the shape of the distribution. Statistical analyses have been conducted using the results of direct imaging surveys to place upper limits on the occurrence rate of giant planets in wide orbits. These analyses generally find that fewer than about 10% of Sun-like and A-type stars host a planet more massive than 5 Jupiter masses at orbital distances between 30 and 300 astronomical units. But the constraints at lower masses and smaller separations are much weaker, and the possibility that a large population of lower mass planets exists at wide separations, undetectable by current surveys, cannot be excluded. The debris disk provides a complementary window into the system's past. We discussed its structure earlier, the warm inner belt and the cold outer belt, separated by the planet-carved gap, but its deeper significance lies in what it reveals about the system's history. The debris disk is a living record of collisions and dynamical evolution. The dust particles that we observe have lifetimes of thousands to millions of years, after which they are removed by radiation pressure, the Poynting-Robertson effect, or mutual collisions. Their continued presence implies an ongoing source of fresh dust, generated by the collisional grinding of larger parent bodies. These parent bodies are the remnants of the planetesimal population that existed during the era of planet formation. They are the survivors, the objects that were neither accreted into the planets nor ejected from the system. Their distribution tells us about the solid inventory of the protoplanetary disk and the efficiency of planet formation. For HR 8799, the total mass of the outer debris belt has been estimated from sub-millimeter and millimeter wavelength observations to be in the range of roughly a few tens of Earth masses. This is comparable to estimates for the Kuiper belt in our own solar system before it was dynamically depleted by Neptune's migration. The inner belt is less well constrained, but its infrared emission suggests a mass of at least a fraction of an Earth mass. The presence of substantial debris belts indicates that the protoplanetary disk was rich in solid material, consistent with the formation of multiple giant planets, and that the planet formation process was not perfectly efficient. A significant fraction of the original solid material was left behind in the form of smaller bodies that continue to collide and produce dust. The debris disk also serves as a dynamical probe of the planet-forming region. The sharp inner edge of the outer belt, at roughly 90 astronomical units, is maintained by the gravitational influence of planet B, the outermost planet, at 68 astronomical units. Numerical simulations of debris disk sculpting show that the location and sharpness of this edge depend on the mass and orbital eccentricity of the sculpting planet. The observed sharpness is consistent with a planet mass of 5 to 7 Jupiter masses and an eccentricity below about 0.1, in agreement with the constraints from direct imaging astrometry and dynamical stability analysis. This provides an independent, complementary confirmation of the planetary parameters derived from entirely different observational techniques. The resonance chain is another aspect of the system that carries implications far beyond the boundaries of this one stellar system. The 1 to 2 to 4 to 8 period ratio is a specific mathematical relationship that must have been established during the epoch of planet formation, when the planets were still embedded in the gas disk and their orbits were evolving due to planet-disk interactions. The establishment of a resonance chain requires convergent migration, meaning the planets must have been moving toward each other, with the inner planets migrating inward more slowly than the outer planets, or the outer planets migrating inward faster. As the orbits converge, the planets pass through the resonance, and if the convergence is slow enough and the eccentricity damping from the disk is strong enough, the planets are captured into resonance. The process must occur sequentially, with each pair of planets being captured in turn, building the chain link by link. This process is deterministic but sensitive to conditions. The migration rate must be slow enough for capture to occur, but not so slow that the disk disperses before the chain is complete. The eccentricity damping must be strong enough to prevent the planets from being scattered out of resonance by close encounters all day, but not so strong that it prevents the eccentricities from reaching the values needed for stable libration. The masses of the planets must be in the right range, too small, and the resonant interaction is too weak for capture, too massive, and the planets open deep gaps in the disk that alter the migration rate and potentially break the chain. The fact that the HR 8799 system hosts a 4-planet resonance chain tells us something profound about the conditions in its protoplanetary disk. The migration was not random or chaotic. It was smooth, gradual, and sustained over a period long enough for all 4 resonance captures to occur. The disk properties, including its mass, viscosity, and temperature structure, must have been within the specific range that allows this kind of orderly convergent migration, and the disk must have dispersed at precisely the right time after the resonance chain was fully established but before further migration could destabilize it. Compare this with the solar system. Our giant planets are not in a resonance chain today. Jupiter and Saturn have a period ratio of roughly 2.49, close to but not at the 5 to 2 resonance. Saturn and Uranus have a period ratio of roughly 2.85, far from any simple resonance. Uranus and Neptune have a period ratio of roughly 1.96, close to but not at the 2 to 1 resonance. The NICE model, the leading theory for the late dynamical evolution of the outer solar system, proposes that Jupiter and Saturn were originally in a 2 to 1 or a 3 to 2 resonance, and that the crossing of this resonance triggered a period of dynamical instability that scattered Uranus and Neptune outward, disrupted the primordial Kuiper belt, and caused the late heavy bombardment of the inner solar system. If this model is correct, then our solar system once had a resonance chain, or at least a partial one, and it broke. The system transitioned from an ordered, resonant state to the disordered, non-resonant state we observe today. HR 8799, by contrast, has maintained its resonance chain. At 30 million years old, the resonance is intact. Whether it will remain intact for billions of years is an open question. Simulations suggest that it can, provided the system is not perturbed by passing stars or other external influences. But the survival of the resonance for 30 million years is already significant. It means that the system has not yet experienced the kind of instability that the NICE model invokes for our solar system. It is still in its ordered phase, its planets still dancing in their original choreography. This comparison between the ordered state of HR 8799 and the disordered state of our solar system highlights a fundamental question about the evolution of planetary systems. Is order or disorder the norm? Are resonance chains the natural initial state of all planetary systems, with subsequent instabilities breaking most of them? Or are resonance chains rare, formed only under specific conditions, with most systems never achieving this level of dynamical order? The answer has profound implications for our understanding of planetary system evolution and for the habitability of planets within those systems. A system that experiences a major dynamical instability may scatter planets into and out of the habitable zone, deliver water to rocky planets through asteroid impacts, or strip the atmospheres of rocky planets through giant impacts. The timing and severity of such instabilities may determine whether a given planetary system can develop conditions suitable for life. The question of time adds yet another layer of complexity. HR 8799 is 30 million years old. Our solar system is 4.6 billion years old, more than 150 times older. We are observing the HR 8799 system in its youth, a snapshot of a planetary system that has barely begun its long journey through cosmic time. The planets are still glowing with the heat of their formation, their atmospheres still settling into equilibrium, their orbits still locked in the resonance that was established during the disk epoch. In 4 billion years, the planets will have cooled to a dim fraction of their current luminosity. The debris disk will have been largely depleted, ground down to dust and blown away by radiation pressure. The resonance chain may or may not have survived. The system will be profoundly different from what we observe today. This temporal dimension is crucial because it means that the HR 8799 we observe is not the same as the HR 8799 that will exist in the distant future. We are seeing this system at a particular moment in its evolution, and the properties we measure are products of that moment. The bright, hot, self-luminous planets that we can detect today are revealing themselves precisely because the system is young. In the fullness of time, they will fade beyond the reach of our instruments, and the system will become invisible. One more collection of dark, cold worlds orbiting an ordinary star, indistinguishable from billions of others across the galaxy. How many systems like HR 8799 exist in this invisible older state? We do not know. We cannot know with current technology. The dark, cool descendants of HR 8799-like systems would be undetectable by direct imaging, too far from their stars for transit surveys, and with orbital periods too long for radial velocity monitoring. They would be ghost systems, structurally present but observationally absent. The Milky Way could contain millions of such systems, remnants of the brief epoch when young stars birthed multiple giant planets in resonant chains, now faded into obscurity. Or there could be very few. The universe keeps its secrets. What we can say is that HR 8799 provides a window into a class of planetary system architecture that we would otherwise know nothing about. Its youth is our advantage. The planet's thermal glow is a gift, a beacon that allows us to study a configuration that would be invisible at any other age. The system is showing us something about the diversity of planet formation outcomes that the transit and radial velocity surveys, with their inherent biases toward short-period planets, cannot reveal. And in doing so, it is reminding us that the universe of planetary systems is far larger, far more varied, and far more surprising than any single detection method can capture. The full truth lies in the synthesis of all methods, all surveys, all wavelengths, all epochs, and even then it will be incomplete. The universe is under no obligation to make itself easy to understand, and yet the system has already taught us something we would not have learned otherwise: that the mechanisms of planet formation are more versatile, more capable of producing extreme outcomes than our theories anticipated. Before HR 8799, no theoretical framework predicted that 4 giant planets could form and survive in a resonant chain at orbital distances of 15 to 70 astronomical units. The models could produce individual giant planets at moderate separations. They could produce multiple planets in close-in configurations. They could produce wide-orbit brown dwarfs and stellar companions. But the specific combination of properties that HR 8799 exhibits fell through the gaps between the models, occupying a region of parameter space that was theoretically unexplored because it was assumed to be empty. This is a pattern that recurs throughout the history of astronomy. Theory is shaped by observation, and observation is shaped by technology. When the available technology can only detect certain types of objects, the theory is calibrated against those objects, and configurations that the technology cannot detect are implicitly assumed to be rare or non-existent. Then a new instrument comes along, capable of probing a previously inaccessible regime, and the universe reveals that the assumed emptiness was merely an artifact of observational limitation. Hot Jupiters were not predicted before they were discovered. Super-Earths were not predicted before they were discovered. Circumbinary planets were considered unlikely. Ultra-short period planets, with orbital periods measured in hours, were not anticipated. In every case, the discovery expanded our understanding of what is possible and forced a revision of the theoretical framework. HR 8799 is another entry in this list. It is a system that was not predicted, that was discovered by a new technique applied at the right time to the right target, and that has forced a fundamental rethinking of the processes that govern the birth of worlds. The theoretical revisions are still ongoing. The debate between core accretion and disk instability, between in situ formation and migration, between single mechanisms and hybrid processes, is far from settled, but the terms of the debate have been permanently altered by the existence of this system. No theory of planet formation can claim completeness unless it can explain HR 8799, and no theory has yet achieved that standard. The observational limitations we have discussed also carry a deeper philosophical point that is worth acknowledging. We tend to think of scientific knowledge as accumulative, each discovery adding a new piece to a steadily growing mosaic. But the study of exoplanetary systems reveals a different picture, one in which each new discovery does not merely add a piece, but reshapes the mosaic itself. The discovery of hot Jupiters did not just add a new type of planet to the catalogue, it forced a complete rethinking of planet formation and migration theory. The discovery of super-Earths did not just add another category, it raised the question of why our solar system lacks them, and whether some entirely different formation channel operates in the inner regions of protoplanetary disks. And the discovery of HR 8799 has not merely added one more system to the census of directly imaged planets. It has posed a challenge to every formation model simultaneously, requiring either fundamental revisions to existing theories or the development of new ones. This is what makes exoplanetary science so exciting and so humbling. Every system we discover has the potential to overturn what we thought we understood. The universe is not repeating a single formula with minor variations. It is exploring the full phase space of possible outcomes, producing systems that span the entire range from familiar to alien, from orderly to chaotic, from minimal to extravagant. HR 8799 sits near the extravagant end of that range, a system so richly endowed with massive, widely separated, resonantly locked planets that it strains the explanatory capacity of our best models. It is a challenge, a mystery, and an invitation, all at once. Part 6. The broader canvas. Let us step back now and consider what HR 8799 means, not just for the science of planet formation, but for our broader understanding of the universe and our place within it, because the implications of this system extend far beyond the technical questions of core accretion timescales and resonance capture efficiency. They reach into the very heart of what we mean when we ask whether we are alone. The question of habitability is rarely discussed in connection with HR 8799, and for good reason. The 4 known planets are all gas giants, with masses of 5 to 10 times that of Jupiter. They have no solid surfaces. Their atmospheres are furnaces of hydrogen and helium, laced with iron clouds and silicate hazes. They are as inhospitable to life as we know it, as any environment we can imagine. There is no plausible scenario in which these planets harbour biology, but habitability is not only about the planets themselves, it is about the system architecture. The arrangement of giant planets in a system determines the gravitational environment experienced by every other object in that system, including any rocky planets that might exist in the habitable zone. In our own solar system, Jupiter plays a complex and still debated role in the habitability of Earth. One long-standing hypothesis holds that Jupiter acts as a gravitational shield, deflecting comets and asteroids that would otherwise bombard the inner planets, reducing the impact rate on Earth to a level compatible with the development of complex life. More recent analyses have complicated this picture, suggesting that Jupiter may actually increase the impact rate on Earth for certain populations of small bodies by gravitationally perturbing their orbits into Earth-crossing trajectories. The true role of Jupiter in Earth's habitability is still a matter of active research. Now consider the HR 8799 system. There are 4 giant planets, each more massive than Jupiter, orbiting at distances of 15 to 68 astronomical units. The gravitational influence of these planets dominates the entire system. Any rocky planet that might exist in the habitable zone of HR 8799, which lies at roughly 1.8 to 3.5 astronomical units given the star's luminosity, would be subject to gravitational perturbations from four massive outer companions. Whether these perturbations would be stabilizing or destabilizing, whether they would enhance or suppress the delivery of volatile-rich material from the outer system, whether they would permit or prevent the formation of rocky planets in the first place, are all questions that depend on the details of the system's dynamical evolution. Some simulations have investigated the possibility of rocky planets in the habitable zones of systems with multiple giant planets. The results are mixed. In some configurations, the giant planets create dynamically stable niches in the inner system where rocky planets can survive for billions of years. In others, the gravitational perturbations from the giant planets render the inner system chaotic, preventing the long-term survival of any terrestrial planet. The outcome depends sensitively on the masses, orbits, and resonant relationships of the giant planets, all of which are known to high precision for HR 8799. A detailed dynamical study of the habitable zone stability in the HR 8799 system has not yet been published, but the tools exist to conduct such a study, and the results would be of considerable interest. The question of whether rocky planets actually formed in the inner regions of the HR 8799 system is separate from the question of whether they could survive there. The protoplanetary disk that gave rise to the four giant planets presumably also contained solid material in the inner disk, material that could in principle have accreted into terrestrial planets. But the gravitational influence of the massive outer planets during the disk epoch may have disrupted the inner disk, preventing the orderly accumulation of rocky material. Alternatively, the inner disk may have been dynamically isolated from the outer disk by the gap carved by planet E, the innermost giant, allowing terrestrial planet formation to proceed undisturbed. The warm inner debris belt, detected at 6 to 15 astronomical units, suggests that some solid material survived in the inner system, but whether it includes planet-sized bodies remains unknown. Even if no rocky planet exists in the habitable zone of HR 8799, the system contributes to our understanding of habitability in a broader sense. The diversity of planetary system architectures revealed by exoplanet surveys has forced us to reconsider what kinds of systems are capable of supporting life. The classical picture, in which habitability requires a system like our own, with small rocky planets in the inner system and well-behaved giant planets in the outer system, may be too restrictive. Systems with very different architectures, including systems with super-Earths in the habitable zone and no giant planets at all, may be equally or even more hospitable, and systems with extreme configurations, like HR 8799, may serve as natural experiments, testing the limits of what is dynamically possible and thereby defining the boundaries of the habitable parameter space. There is also a philosophical dimension to the study of HR 8799 that should not be overlooked. The system challenges us to confront the limits of our predictive power. In physics, we are accustomed to the idea that the fundamental laws are simple and universal: gravity, electromagnetism, quantum mechanics, thermodynamics. These laws apply everywhere, at all times, in all circumstances. But the outcomes they produce are not simple. The same laws that govern the hydrogen atom govern the formation of galaxies, the evolution of stars, and the birth of planets. The complexity of the outcome is not a reflection of the complexity of the laws. It is a reflection of the complexity of the initial conditions. Two protoplanetary disks, both governed by the same physics, can produce radically different planetary systems depending on their initial mass, composition, temperature, angular momentum, and the details of their environment. HR 8799 and our solar system are products of the same physics, but different initial conditions. And the range of possible initial conditions is so vast that the range of possible outcomes is effectively infinite. This insight has a humbling corollary. We often speak of the predictive power of science, the ability to forecast outcomes based on fundamental principles. And in many domains, that power is extraordinary. We can predict the orbit of a satellite to millimeter precision. We can predict the products of a nuclear reaction. We can predict the evolution of a star over billions of years. But we cannot, at present, predict the architecture of a planetary system from the properties of its natal disk. The initial conditions are too complex, the processes too numerous, the interactions too nonlinear. We can simulate possible outcomes, explore parameter spaces, and identify trends. But we cannot point to a molecular cloud and say with confidence, this cloud will produce a system with 4 giant planets in a resonance chain at wide orbital separations. The connection between initial conditions and final outcome in the domain of planet formation remains obscure. This is not a failure of science. It is a recognition of the genuine complexity of the natural world. Planet formation is a process that spans 10 orders of magnitude in spatial scale, from micrometer-sized dust grains to astronomical unit-scale orbits. It involves physics from at least a dozen different subdisciplines: thermodynamics, fluid dynamics, radiative transfer, magnetohydrodynamics, solid mechanics, collisional dynamics, gravitational dynamics, and atmospheric chemistry, to name only the most prominent. It plays out over millions of years, with critical events that occur on timescales of hours, such as a collision between 2 planetesimals, or seconds, such as the gravitational capture of a passing pebble. Simulating this process from beginning to end with full physical fidelity is beyond the capacity of any computer that exists today. What we have instead are approximations, models that capture some aspects of the physics while simplifying others, simulations that resolve some scales while parameterizing the rest. These models have been enormously productive. They have explained the broad strokes of planet formation and reproduced many of the observed properties of exoplanetary systems. But they have not yet explained HR 8799, and that failure is instructive. It tells us that somewhere in the chain of approximations and simplifications, something important is being lost. Some piece of physics, some process, some interaction that matters for the specific outcome of HR 8799, but not necessarily for the typical outcome, is either absent from the models or represented with insufficient fidelity. Finding that missing piece, or pieces, is the challenge. And it is a challenge that may take decades to resolve, because it requires not just better simulations, but better observations, better laboratory measurements of grain growth and collisional dynamics, better theoretical frameworks for understanding the interaction between forming planets and their natal disks, and possibly new physical insights that have not yet been imagined. In the meantime, HR 8799 stands as a monument to the universe's capacity to surprise us. It is a system that no one predicted, that no model can yet fully explain, and that has reshaped the questions we ask about how planets are born. It is a reminder that the universe does not exist for our convenience. It does not arrange itself to match our expectations or conform to our theories. It simply is, in all its bewildering, infuriating, magnificent complexity. And the greatest gift it offers us is the opportunity to be wrong, to be surprised, and to learn. The 4 giant planets of HR 8799 will continue their slow, stately dance around their star for billions of years to come, long after the last astronomer who studied them has turned to dust. Long after the telescopes that observe them have been superseded by technologies we cannot yet envision, the planets will still be there, orbiting in their resonant chain, their atmospheres slowly cooling, their gravitational ballet endlessly repeating. They are indifferent to our curiosity, unmoved by our confusion, oblivious to the theories we construct and discard in our attempts to understand them. But we are not indifferent to them. We are drawn to them, compelled by the same impulse that has driven every human inquiry into the nature of the cosmos, the desire to understand, to explain, to make sense of a universe that is under no obligation to make sense. HR 8799 is a gift and a challenge, a beacon and a mystery. And the story it tells is far from over. The human dimension of this story is worth acknowledging as well. Behind every observation, every simulation, every theoretical paper, there are people, astronomers who spent years developing the instruments and techniques that made the discovery possible. Graduate students who wrote the code that subtracted the starlight and revealed the planets. Theorists who stayed up late running simulations that explored millions of possible configurations, searching for the narrow parameter space where stability permits existence. Observers who traveled to mountaintop telescopes in Hawaii, Chile, and the Canary Islands, spending long nights in control rooms, coaxing photons from a faint star 129 light-years away. The study of HR 8799 is a collaborative enterprise of extraordinary scope, spanning continents and decades, involving hundreds of researchers whose collective effort has produced the understanding we have today. And yet that understanding is still incomplete. The honest answer to the question of how this system formed is that we do not know. We have hypotheses, constraints, models, and simulations. We have narrowed the possibilities. We have ruled out some scenarios and identified the challenges facing others. But we have not solved the problem. The formation of HR 8799 remains one of the open questions of modern astrophysics, a question that sits at the intersection of stellar physics, disk physics, planet formation theory, atmospheric science, and celestial mechanics. It is a question that will be addressed by the next generation of telescopes, the next generation of computer models, and, most importantly, the next generation of scientists, young researchers who are today studying physics and astronomy, and who will, in the coming decades, bring fresh perspectives and new ideas to a problem that has resisted solution for nearly 2 decades. Let us return one last time to the light that left the HR 8799 system 129 years ago, when it began its journey across the interstellar void toward us. In the year that light departed, roughly 1897, Guglielmo Marconi was demonstrating the first practical radio transmissions. The electron had just been discovered by J.J. Thomson. The concept of a planet orbiting another star was pure science fiction, a speculation without a shred of observational evidence. No one on Earth could have imagined that the photons streaming away from a nondescript star in the constellation Pegasus carried information about 4 giant worlds larger than anything in our solar system, locked in a gravitational dance of breathtaking precision. Those photons traveled through the emptiness of interstellar space for more than a century, crossing distances that defy human intuition. 129 light-years is roughly 1.2 quadrillion kilometers. If you could drive a car at highway speed, it would take you approximately 1.4 billion years to cover that distance. The photons, traveling at the speed of light, the fastest speed permitted by the laws of physics, needed 129 years. And during those 129 years, the universe changed. Empires rose and fell. 2 world wars reshaped the map of the globe. Humanity split the atom, walked on the moon, decoded the genome, and built machines capable of processing billions of calculations per second. And all the while, the photons flew onward, indifferent to the dramas unfolding at their destination, carrying their message in silence. When those photons finally arrived at the Keck Observatory on the summit of Mauna Kea in Hawaii, they were captured by a 10-meter mirror, focused by adaptive optics systems that corrected for the turbulence of Earth's atmosphere 60 times per second, filtered through a coronagraph that blocked the overwhelming glare of the central star, and recorded by a detector cooled to cryogenic temperatures. The entire technological apparatus that received those photons, from the telescope to the detector to the computer that processed the images, was the product of centuries of accumulated human knowledge and ingenuity. The photons did not know they were being received. They did not care. They simply arrived, as they always do, carrying their encoded information to whoever or whatever happened to be looking. And what they revealed was extraordinary. 4 points of light, each one the thermal glow of a giant planet, each one a world in its own right, with an atmosphere and a history and a future that extends billions of years into the cosmic timeline. 4 worlds that we cannot visit, cannot sample, cannot touch. 4 worlds that we know only through the light they emit, decoded through the combined efforts of thousands of scientists working across decades with instruments of astonishing sophistication. This is the essence of astronomy, Distilled to its purest form, we cannot touch the stars, we cannot visit the planets of other systems, we cannot collect samples or run experiments in situ. All we have is the light, the photons that travel across the void, carrying information encoded in their wavelength, their timing, their polarization, their intensity. From these photons, we reconstruct worlds. We infer masses and temperatures and compositions. We deduce histories and predict futures. We build models and test theories and argue about interpretations, all from the light. It is the most indirect form of knowledge imaginable, and yet it has revealed a universe of staggering complexity and beauty. HR 8799 is one jewel in that revelation, but it is a jewel that shines with particular brilliance because it shows us something we had never seen before and still do not fully understand. The 4 planets continue their orbits as you hear these words. Planet E, the innermost, completes its circuit in roughly 57 years. It has completed perhaps half an orbit since it was discovered. Planet D, at 24 astronomical units, takes about 115 years. It has traced perhaps a sixth of its path in the time we have been watching. Planet C, at 38 astronomical units, requires roughly 230 years. It has moved through perhaps an eighth of its orbit since 2008. And Planet B, the outermost, at 68 astronomical units, takes approximately 460 years to complete a single revolution around its star. It has covered less than a 20th of its orbit in the entire history of our observations. We will not live to see any of these planets complete an orbit. Our children will not see it. Our grandchildren will not see it. The orbital period of Planet B is longer than the entire age of the modern scientific enterprise. It was last at its current position in its orbit roughly in the year 1568, when the Dutch Republic was fighting for independence from Spain, and Tycho Brahe was a young man who had not yet built his observatory. It will return to this position around the year 2488, in a future so distant that we cannot meaningfully imagine what human civilization will look like or whether it will exist at all. And yet the orbit will continue. The resonance chain will hold, the 4-to-8 ratio ticking along like a cosmic metronome, each planet pulling on its neighbours, each orbit adjusting to the perturbations of the others, the entire system maintaining its delicate balance through the relentless precision of gravitational mechanics. There is something deeply moving about this persistence. The planets do not care about our theories. They do not know that we have been arguing for nearly 2 decades about how they formed. They simply orbit, as they have orbited since they coalesced from the gas and dust of a protoplanetary disk 30 million years ago, and as they will continue to orbit for billions of years to come. The light from HR 8799 will continue to stream across interstellar space, carrying its encoded message to any observer who cares to look. In 129 years, the photons that are leaving the system right now will reach Earth. The telescopes that receive them will be unimaginably more powerful than anything we have today. The astronomers who analyze them will have tools and techniques and theoretical frameworks that we cannot foresee. They will know things about this system that we can only dream of. They may have solved the formation puzzle. They may have discovered additional planets, moons, or rings. They may have measured the atmospheric compositions with sufficient precision to determine the formation mechanism beyond any doubt. Or they may have discovered that the puzzle is deeper than we imagined, that the system harbours secrets that our current conceptual framework is not equipped to comprehend. Whatever they find, the system will still be there. 4 giant worlds, spinning through the darkness, their iron clouds catching the light of a young star, their orbits interlocked in a ratio of 1:2 to 4:8. The most spectacular directly imaged planetary system ever discovered, a testament to the creativity of nature and the stubbornness of human curiosity, a reminder that the universe is vast beyond comprehension, old beyond reckoning, and strange beyond anything we have yet imagined. We began this story with a question: how do you see what should be invisible? The answer, it turns out, is that you build better eyes. You invent technologies that extend your vision beyond the limitations of biology. You develop mathematical techniques that extract faint signals from overwhelming noise. You collaborate across continents and decades, pooling your skills and your knowledge and your determination. And then you point your new eyes at the sky, and you look carefully, patiently, persistently, willing to be surprised, willing to be wrong, willing to spend years interpreting a handful of photons from a system that is so distant and so different from your own that it might as well exist in another universe. The scientists who study HR 8799 are doing something that humans have done since we first looked up at the night sky. They are trying to understand their place in the cosmos. The methods have changed. The questions have become more specific, more technical, more mathematically sophisticated. But the fundamental impulse is the same. We look at the stars and we ask, what are they? How did they get there? Are there worlds around them? Are they like ours? Could they harbor life? Could they harbor intelligence? Are we alone? HR 8799 does not answer all of these questions. It does not answer most of them, but it answers one definitively and profoundly. The universe can build planetary systems of extraordinary complexity, systems that challenge our understanding, systems that defy our predictions, systems that humble our theories. Whatever else is out there, whatever other wonders and mysteries the cosmos contains, we know that it contains at least this: 4 giant planets, dancing in resonance around a young star, 129 light-years from home. And the fact that we know this, that we have reached across the void and decoded the message carried by ancient photons, is itself a kind of miracle, not a supernatural miracle, but a human one. A miracle of ingenuity and perseverance and the unquenchable desire to know. The dance continues, the light travels, and we, small and brief and improbable, are watching.